Okay, look up here. So on page 295, what you're going to see is potassium, and that's a solid, it's a metal, and zinc chloride. How come I didn't say zinc dichloride? Because that's a prefix, and we don't add prefixes to ionic compounds. How do I know that this is an ionic compound? How do I know this right here is an ionic compound?
Because they're close together on the periodic table.
Because they're far apart on the periodic table, right? Zinc and chlorine are on opposite ends of the table, right?
Yeah, man.
Cool? So this is a metal bonded to a non-metal, so that's how we know it's ionic. When we name ionic compounds, we don't use prefixes, so this is just zinc chloride. So the question here is, will there be a reaction? And it turns out, actually, if you look at the table on 293, there's a way to know whether or not there will be a reaction. We just use the activity series. And this is just the reactivity of different metals. All right, so it turns out that potassium is much more reactive than zinc is. So it's going to replace it. So what do we get as a product? What's the product?
Potassium chloride.
Exactly, potassium chloride. So we get potassium in zinc's position, and there's a chlorine bonded to it. So here's what you need to do now. Now that you have this new formula, you have to determine how many of each thing you need. How many potassiums you need and how many chlorines you need. What's the oxidation state of chlorine? 1 minus, exactly. It makes one bond, so how many potassiums will you need to make this bond? Just one. And potassium, what's its oxidation state?
+1.
1 plus. So how many chlorines will you need to make this bond? 1. All right, so remember, you crisscross these numbers. That's how you figure out how many of each thing you need in a new bond. So the finished formula is KCl. And this is going to be aqueous. It's going to be dissolved in water. KCl is soluble.
Wait, what about the Cl2 though? What happened to that? The 2.
So we're going to have to balance the reaction. After we've got the equation written down, we're going to balance it. That's a great question. So the zinc is now free. It's all by itself. It's just zinc. And it's a metal, so it's solid. Right? So in this reaction, in this new equation, I have to balance it. There's 2 chlorines, as Tom pointed out. There are 2 chlorines on this side. There's only 1 here. So what do? I put a 2 in front. Good. Now there's 2 potassiums and only 1 over here. So I have to put a 2 in front of this one. And the zincs are okay. So this is the finished formula for the reaction that would take place if you put potassium metal in a solution with zinc chloride. Cool? The way you figure that out is you look at your table. I'm going to hand it to you in a second. This is the activity series. All right, just one you can use as reference for the next couple of weeks. All you do is just look on this and you see that potassium is more reactive than zinc. That's it. And so you know a reaction will take place. What about for number, will there be a reaction for number 22 on page 295? Would there be a reaction? 22 says chlorine gas plus HF. Would there be a reaction? Is chlorine more reactive than fluorine? It's not.
Wait, I thought it was supposed to be hydrogen.
So there's 2 types of, this is called single replacement, right? We're just replacing one thing. It's called single
You
replacement.
just pick whether you know hydrogen.
There's only 2 types. There's when a metal replaces a metal, or when a non-metal replaces a non-metal. In this case, chlorine's a non-metal. It might replace fluorine if it's more reactive. Look on the chart on 293. Which one's more reactive, chlorine or fluorine? Fluorine is more reactive. So there's no reaction. This does not go forward. Nothing happens. There's no reaction. Is that okay?
Which one is the reactivity?
That's all on 293, that little chart in the corner on 293. And I'll give you a separate sheet here that also has that on there. Okay. And on this is also your problem set for today. All right, so here's a question for number 23. Is iron more or less reactive than sodium? That's the question. Is iron more or less reactive than sodium? It's less reactive. On your activity series, right? Sodium is down here. I mean, sodium's up here. And iron's down here. So sodium's actually more reactive, so nothing will happen. There's nothing going on here. There's no reaction. If you put these things in the same solution, nothing will happen. Because iron's less reactive than sodium. Is that all right? Let's do something a bit more practical, okay? So right here, I've got a little magnesium on this watch glass. All right. If I add hydrochloric acid to it, answer me this: is magnesium more or less reactive than hydrogen? Look at the activity series I handed you. Is magnesium more or less reactive than hydrogen? It's more reactive. So would you expect if I added hydrochloric acid to this magnesium right here, would anything happen?
Yes.
Yeah.
Yes. There will be a reaction. If I can get any hydrochloric acid. All right, see the physics? Now the question is, what gas is that? Let's think about the reaction that we're seeing take place right now. If I put magnesium solid and hydrochloric acid together, the question is this: is magnesium more reactive than hydrogen? We said it is. So this is going to replace the hydrogen. All right, so what's the product? What product do we get? Exactly, magnesium chloride. Good. All right, we formed a new bond. What's the oxidation state of chlorine? 1 minus. So how many magnesiums will I need?
1.
What's the oxidation state of magnesium? 2 plus. So how many chlorines will I need? 2. All right, so that's your finished formula. Mg1Cl2. What happened to the hydrogen? It's released, right? And hydrogen never exists all by itself. It's always gonna form a diatom. So this is gonna be hydrogen 2. It's gonna bond to itself. And this is a gas, as you just saw. That smoke coming off the reaction, that was hydrogen gas. Hydrogen gas is naturally abundant in the atmosphere. It always occurs as H2. Is this all right?
There's never H1.
Never H1. Unless you're talking in aqueous solution. In water, there is essentially H1, more or less. There's H3O plus. So in aqueous solution, we talk about protons being handed back and forth. But it's really H3O plus. But anyway, that's a digression. So how do we balance this equation? You can see on the right-hand side, we've got 2 chlorines, and up here we've only got 1. What do? Put a 2 right here, right? And we've got 2 hydrogens here and 2 here, so that's good. What about magnesium? Is that all set? Okay. So on your problem set, this is what you need to do. All right? Just like this, you write the new products. You name this product. What's this called? Magnesium chloride. It's an ionic compound, so you don't use the prefixes. You wouldn't say magnesium dichloride. That would only be if it was a molecular compound. And molecular compounds are only those between nonmetals and nonmetals, right? In your lab groups, work on your problem set. Okay? First one, most accurate answers by the end of class, 2 points on your last test. Okay? Work in your lab groups, work together. Tom, what was your question?
Like right here. So lithium and what?
So, chlorine, 1 minus. So that means it's one bond, that's with a bond, the one next to it. Plus, and this is bond twice as much as CO.
So then put
Put the top of this.
For most reactors. So what was it?
oh no, it would be opposite.
What is that?
No.
Living is really reactive, right?
Well, no, I want to do first you have to, find the product.
So what's the oxidation?
Calcium. It's pretty reactive.
Then you put the calcium. Yeah, but you have to still put in at least plus H2. What's the
Is that in order for this to
So now you can see you got a product. So there's two different things.
right? Li2.
Exactly. So calcium's free now, all by itself. Just CO and solid.
We use the plus filter.
Of course.
Still in the
So is it like one by itself and it's more
Right. Yes. Yes. So again, this is called single replacement. So you're just wondering, is this metal going to replace that metal? That's your only question. And the only way it's going to be able to do that is if it's more reactive
And then,
as a species. So here's calcium. Here's lithium. Lithium's way more reactive. So we've been able to replace
did you
it.
figure out
Well, should we just ask if that's correct?
and then
Literally take its position
do plus C.
plus calcium. Yes.
It is right.
and then you, make
It is.
some
Perfect. Very nice. Very nice.
plus you.
Potassium is second terminal.
Look at the metal. So if the species here that you're reacting with is metal, the question is, will that metal be more reactive than metal that's already in this thing? So it's either a metal replacing a metal, or a non-metal replacing a non-metal. That's it. There's only two types of single replacement. Yes. Yep.
So the first one, they're just
Gives you metal.
Right, so that's exactly right. But now you make sure we have enough.
yeah.
So, just think about this new complex associations in
K2Cl. Is there, oh wait, there's two of them.
It's
Oh
in
wait,
group
so.
16, right? So it's going to tend to make two bonds to get to the group.
Oh, you're right.
With hydrogen.
Yeah.
Two bonds. So how many?
Cause you gotta balance it.
Big two.
So it's Li2.
Wait.
Yeah.
For the second. So, is that, how do I set it up first?
Yeah, same thing.
And, yeah, what, add
Yep.
two right here.
Potassium.
Yeah, balance all of them.
You also can see that calcium H2 plus. So
When it's all by itself,
I don't know.
you don't even need to think about that. That's only just to
I was
determine.
confused with movement, so I was like.
Oh, you don't need
No,
that.
no, that makes sense.
Right, there.
So wait, yeah, it's just five.
Yes.
11 plus 8.
Where did you get the,
Wouldn't it be SO4?
oh, wait, no. Oh, I knew that. I usually.
Okay, so this is correct.
I thought you have to replace it.
Oxygen has two minus oxidation. It'll make two bonds, right? So you need to. Yeah. There you go. Yeah. That's the finished formula. Calcium solid. No. Well, now, right, you need to make sure it's balanced. So if there's two liquids on this side, then you have to put two right here. Conservation advantage.
Give them beer and strong sound.
Like if I put here, it's not.
So that would be 4 lithiums, and then you have to put 4 right there. Does that make sense?
So there's just
Well, you gotta make sure the lithiums are
I
balanced.
do water bottles.
There's 2.
That dilute because one comes from.
Yeah.
And you don't even use this
So yeah, we'll do it. How is but this record was really long.
If you did,
So
let's
short.
be hypothetical for a second. Put a 2 there. Now there's 4 lithiums.
You do.
So on this side, 4 on this side. So on the product side, there's an arrow indicating the reaction went forward. This is called the product reaction.
Are you gonna?
Okay.
Hell, you can.
So why don't you erase that? Alright, so if you did put a 4, if you did put a 2 here, now there's 4 lithiums, so you need 4. If there's no 2, then there's 2 lithiums, so you need 2.
Put any number in the equation.
You can't put any number. It has to be equal on both sides. It's called the first law of thermodynamics. You've been actually doing that for like a week. See that all last week.
Yeah. Why did she?
So listen, in a finished formula, you don't put the oxidation states. That's only written, so you need to figure out what this formula is. So you don't have to have these in the finished formula.
The way she. So I could.
So when calcium's alone, you don't have to think about the oxidation state, because that's only there to help you think about how many bonds it is. And it's not making it.
Well, I have to know about that. So like,
Right, so again, the oxidation state is telling you how many bonds something makes. It is not making any bonds. So there's just one. So then there would just be one. That's it.
So that test we took
Yeah.
from Friday, and that's missing some stems. So I got only 6
Okay, so I did you take it late?
Yeah, but I did take it.
Okay, let me check. Anybody still completely stuck? No idea what's going on?
I sort of understand it, I just don't know if when I replace copper with elements.
Yeah.
Do I bring the O4 or just one option?
So that's sulfate.
Hey,
Okay, so what about the
no, you're making 2 minus. Is it 2 minus? Okay, I was looking.
I just don't know like it's do I bring do I just bring one seven? So
Let me see if I can answer that. Let me see if I can answer that for a second.
Yeah, right? I know, like whatever stuff arrives.
No. That's, if you have it balanced, you use coefficients. That's the formula. You can't mess with that. That is what it is. Right. Yep. All right, a couple things up here. So, first of all, for number, let's look at zinc chloride, okay? Let's just think about what this molecule looks like for a second. So zinc, in this case, has a +2 oxidation state. So there's 2 plus. It's given up 2 electrons to chlorine, and chlorine now has a full octet and it's negative. And there's another one over here, and it's got a full octet, and again, it's negative. These things are stuck together because they're oppositely charged. This is an ionic compound. Okay? So, even though there's 2 chlorines, when you go to make another bond with potassium, if potassium has a 1+ oxidation state, if it gives up 1 electron, how many of these chlorines is it going to bond with?
What was the question?
1. It's only going to take one of these. It can only bond with one of them. All right? So you're forming a new bond with potassium, and potassium can only make one bond. So you're only taking 1 chlorine. So listen, this is the finished formula. KCl is the finished formula because I need one of these and I need one of those. KCl is the finished formula. I can't change that. I cannot put this. That's a different molecule. All right? If I want to change the number of chlorines after this reaction has taken place, I use a coefficient. Now I've balanced this. We started with 2 chlorines. We end with 2 chlorines. So for every zinc chloride you start with, you're going to make 2 potassium chlorides, 2 distinct, different molecules. This is the formula, KCl. This is a coefficient telling you you're going to have 2 KCl's when you finish the reaction. Does that make any sense? Oh, okay. Second thing is this, just to do a little bit harder oxidation state stuff. On number 3, aluminum, that has a 3+ oxidation state. And sulfate is a polyatomic ion. It has a 2- charge on it. How many aluminums am I going to need? 2. How many sulfates will I need? 3. Okay? You crisscross those numbers. The sulfate comes as a unit, you can't break it up. Okay? Does that make sense?